Let's continue with our story. If you missed part 1, there's a link in the description. You have an idea and would like to test it to see if it'll work. You think all bananas grow pretty much the same, so the proportion of banana peel to edible fruit will be roughly the same no matter what. This assumes that no matter what shipment comes in, what season it is, or what the size or ripeness of the bananas are, the peel will always make up about X% of the total weight of the banana. Therefore, you can program an algorithm in the cash registers that'll take the total weight of the bananas, subtract the predicted weight of the peels, and calculate the price based on the net weight. That's tricky though. If the predicted banana peel weight is too high, the store will be losing money. And if it's too low, customers will be getting ripped off and you'll be failing in your goal of making happy customers. And don't forget disputes. Sooner or later, someone will question your calculation. Therefore, you need to be confident that your calculation is accurate. To do that, you have to design an experiment to test your assumption or hypothesis. You want to collect bananas, weigh them whole, then peel them and weigh the edible fruit that's remaining. This will allow you to calculate a proportion of peel weight to total banana weight. You then get an employee to collect 30 bananas, making sure to get green ones, brown ones, yellow ones, big ones, small ones, medium-sized ones, to make sure that you cover the spectrum of variation you think might exist. The employee then weighs the bananas and records the results, which looks something like this. The average, or mean, proportion of banana peel weight to total weight is calculated by adding up the result for each sample and dividing the sum by the total number of samples. In this case, we see that, on average, 14.82% of a banana's weight is the peel, but you're not ready to program the cash registers yet. If you were to plot each result on a histogram, it would look like this. You see that most of the banana peels were about 14.82% of the total weight. The mean is a way of measuring where the center of your data is. But notice that the data ranges from 8.12 to 22.98. That's quite a difference. So saying all banana peels are 14.82% of the total weight will be close most of the time, but really far off some of the time. So how do you know how much of the time you'll be correct? The central limit theorem states that the more samples you take, the more normally distributed your data will be. On a normal distribution, the curve will look like this. As you see, the mean is in the center. The standard deviation is a measurement of variation that measures the average distance a data point is from the mean. In this example, our standard deviation is 2.85. This means that one standard deviation above the mean will be 14.82 plus 2.85, or 17.67. And one standard deviation below the mean will be 14.82 minus 2.85, or 11.97. Statisticians use the Greek letter sigma to denote standard deviation. On a normal distribution, 68.26% of your data will be within plus or minus one standard deviation of the mean. So even though we say that all banana peels take up 14.82% of the total weight of a banana, the actual value will be somewhere between 11.97 and 17.67, 68% of the time. That's more than half. So do you see how measuring just the mean is not descriptive enough to make a good decision? Well, what about the other 32% of the time? Well, 95.44% of your data will be within plus or minus 2 standard deviations, and 99.73% of the data will be within plus or minus 3 standard deviations. It's important to understand the concept of standard deviation. For example, Let's say we sampled another 30 bananas and the peel proportions were like this. The mean is exactly the same as the original set of 30 bananas, 14.82. If we ignored standard deviation, we'd conclude that the second set of bananas had the exact same peel proportion as the first set of bananas. However, look at the standard deviations. Our original set of bananas had a standard deviation of 2.85. The new set of bananas had a standard deviation of 10.26. So 68% of the time, the actual peel proportion will be between 4.56 and 25.11. So using 14.82% won't tell you much at all. A general rule of thumb is to look at the 95% confidence interval. In this case, the confidence interval is between 13.75 and 15.88. What that means is that we are 95% confident that the true mean of banana peel proportions is between 13.75 and 15.88. It is not saying that 95% of our data will be between 13.75 and 15.88. The golden question now is how much money this uncertainty will cost. If we calculate the peel proportion at 14.82%, but it's really 13.75 or 15.88, what's the cost difference? Pause the video if you want to go over the details, because I'm not going to. But basically, you determine that the cost difference to your store or to the customers is half a cent per pound. You feel like this is an acceptable risk, and you check legal regulations and determine it's okay. So you move on with your experiment. Now remember, this is a fictional example. I'm not claiming to know anything about legal regulations for doing this.